Every day, we interact with perfectly smooth glass screens. The physical mechanics powering our devices are hidden behind interfaces designed to be effortless and invisible. For students, this black box design makes technology feel like magic. Fundamental concepts like binary code and data transmission become abstract ideas rather than physical realities. To understand how the digital world communicates, we have to look past the screens and examine the raw physical logic beneath them. Educator Haseen Ben-Haboush uses a tactile approach to solve this. He believes that grasping computer science requires building the hardware with your own hands. In his classroom, students set aside modern devices to build a functional telegraph using microbits and block programming. It turns out that the most effective way to understand the modern internet is to reverse engineer the 19th century. The telegraph is the world's first true digital communication system. This mechanical lever and contact point represent a binary choice. Morse code uses these physical dashes and dashes under the same logic that modern computers use ones and zeros. When the hand presses the key, it completes an electrical path. This creates a discrete pulse of energy that travels the length of the wire. This physical connection, on or off, is the equivalent of a single bit of data. As wires stretched across hundreds of miles, engineers faced a problem. Electrical pulses naturally lose their strength as they travel through iron or copper. They solved this with the relay. This is an electromagnetic switch designed to be sensitive enough to detect even a very weak incoming signal. Once triggered, it uses a local battery to send a fresh, high-power pulse into the next section of the line. To cross the ocean, these wires required insulation. Engineers used gutta-percha, a specialized natural latex, to protect the raw copper from the surrounding saltwater. Engineers also developed duplexing, a method of balancing the circuit's resistance so that signals could travel in both directions simultaneously without crashing into each other. These methods, relays to boost signals over distance and duplexing to manage two-way traffic, address the same core challenges of signal loss and bandwidth that modern networks handle today. Running this network required a massive, organized infrastructure of offices and service counters to manage the flow of messages. In these offices, operators performed the manual work of receiving, transcribing, and resending data. Their work ensured messages were redirected correctly toward their final destination. Pioneers like Samuel F.B. Morse designed the system with the ambition of turning electricity into a worldwide communication web. This 19th century combination of human labor and mechanical hardware established the first practical rules for global data exchange. Today, the massive cables running under the ocean operate on principles very similar to the simple wires on these students' desks. The students must translate the alphabet into binary code to create and send their own messages. They transmit this data through physical threads or via radio signals using the microbits they have programmed. Abstract math, like converting binary to decimal numbers, becomes intuitive because the students can see the physical result of their logic. The telegraph makes the invisible mechanics of our digital age tangible. By stripping away the modern interface, students find that the binary logic of the Victorian era is the same logic used in the code of today.